Okay, so it's my great pleasure that we have here Jose Renau from UC Santa Cruz. Jose is a professor of computer engineering at UCSC. His research focuses on computer architecture, including design effort metrics and models, infrared thermal measurements, low power and thermal aware designs, process variability, thread level speculation, FPGA ASIC design, fluid pipelines, PyRope, a modern hardware description language that he might talk to us a bit about today. Yeah. And live flows that improve the productivity of hardware designs. He has a PhD in computer science from UIUC. And today he'll be talking to us about ways to very quickly recompile a design within, I think, under 30 seconds or so. This is, I'm sure, very, very exciting to many of us.
Thank you for the introduction. So one question, do we have any remote people to making questions or not? Not clear.
Not for questions, I think.
Okay, just to record.
The talk will be recorded. So.
Okay. Thank you for the introduction. So stop me if you have any question, so we can go over that. So what is the work that I do? I'm a computer architect, but what I'm going to be talking is about the live hardware development cycle that we have at Santa Cruz. So before a little introduction, what do computer architects typically care? So most of my papers, they are typical computer architecture. So I care about two axes. When I do an architectural change, I may have a performance improvement, or I may have a power thermal. And there is a trade-off, and you go over that. The truth is that most of my effort is being on the third axis. When I do an architectural change, I want to see not only the power and performance, I want to see the power and performance, but I want to see what's the complexity, how much, I want to do it faster, or how to solve it. So I have things like releasing beta cores, buggy processors to market and be able to patch them, our metrics to estimate design time. But this is not what I'm going to be talking today. It's addressing this axis, but it's not about those techniques. So what is the challenge that I'm trying to address is that chip design is a very slow task. Simulations are slow, RTL, simulation, emulation, verification is painful, and synthesis is even slower. So why did I start to work on this? Just to give a little background, like around 8 years ago, we were doing an out-of-order processor at the university. And we have to do many respins in order to increase frequency, many issues to improve the finding bugs. The summary was that the tools were horrible. And so they said, okay, instead of building the processor, let's build first the tools, and then we'll go back to the processor. So someday I'll go back to the processor. For the moment, I'm still on the tools. So what is the focus that I'm having for the complexity? Is what I call a live development environment. So what is this live? For me, live is the opposite of a batch. In live, you try to maximize the developer utilization. And you want to have response time in the order of a few seconds. If you have a batch, you care about the computer utilization. In a way, the batch systems, they were designed for Fortran, very slow compilation systems. I don't care about using 20 or 30 computers. Computers are cheap. I don't care about wasting resources. I just want to maximize the developer utilization. So why do we need to go live? And why these few seconds goal? Is in a way we are all Doris. We have short-term memory to solve problems. We only can solve problems using the short-term memory. You cannot use long-term memory to solve problems. Your short-term memory, it usually lasts 2 to 15 seconds. You are superhuman, you can do 30. In my case, I cannot get there. And if you want to do any problem, you have to have short-term memory. That's the reason why you are working and you have a phone call, your productivity, there are so many works that productivity goes down. It's not the phone call that you wasted your 30 seconds, 1 minute, it's that you lost the short-term memory. And then you have to rebuild it to work it. So what you want is the tools to give you feedback, ideally in the 1-2 seconds. That's what you want to increase productivity. I still cannot reach that, but that's my goal. Now I'm at least in the 15-30 seconds what I'm trying to do. So I don't want to get microsecond response. I want to get in the order of a few seconds. Now, just curious, who is going in live and computers? So you Google around, you look Google live coding. what you will find is like some people who do parties, they put together and they program music and they interact with the music on the fly. I'm not doing any music, not a musical person, but it's the same concept really. What I want is be able to tune the program and very fast, quick feedback, be able to get results. And by program here, I'm talking about verilog. So I'll be able to tune the verilog and get fast feedback results and keep doing the iterations very fast. Very different from the flow that we are used now. Now, live programming, because it's useful for the human short-term memory, you also have it for teaching. So it's common that most of the teaching platforms, they use JavaScript or they use Python, and then you have a very interactive environment because it helps you to learn the concepts, not to have a slow compilation process. You are my kid who is 9-year-old, she recently did a class in programming, it was with JavaScript, and it was a very interactive environment. Drawing lines, moving circles, doing for loops. So there are many programs who have this read, eval, print, lab. So what is the current FPGA flow? I'm sure everybody, I don't know if everybody here knows it, but I'm pretty sure that some of you have. And usually the typical flow is that you edit some changes and you have a person doing the code. Then if you are on the ASIC, you have a backend engineer. You don't even run the backend tools for you because you're not going to run DC and ICC. They are going to run it. And if the backend team is like amazing, they will give you feedback in minutes to hours. More likely, they will give you feedback once a week. So you do commits, they will pull out, they will do the synthesis flow, and you will see on a repository a week later. And when you have doubt, you sit together and you start to query with the typical commands if you have a good backend team, and then you can see where's your critical path and get feedback information. And you do your iterations. So those are very long iterations. So you can do it, that's what industry does now, but I don't think it's great. So this is a little bit of motivation to understand what's going on. So let me show you what is the current state of the art for FPGAs. So what I'm trying to do is incremental synthesis, place and route for ASICs and FPGAs. In ASIC, 0. There is nothing. The only thing that you can do is ECO, engineering change order. Those are designed to minimize the amount of gates done. They are slower. They are not designed for speed. They are designed to minimize the speed, number of gates change. So they are not fast. So in FPGA there is something. At least you have the option to enable something. And this is with the latest tools. The data we gathered like 6 months ago. So maybe there is a new early release or something, but really 6 months ago data. So what do we have? We have a design. We changed nothing. We just touched a file. So in theory, it should be 0 time because we didn't do anything. So what do we have? We have 2 flows. Flow 1 is Xilinx. Flow 2 is Quartos. The black dot is the time it takes for doing full. And we divide in synthesis, place, and route, the breakdown of the time for that design. Remember, there's no code change. So in theory, there should be some black dot, and then it should be, if the incremental were working nicely, you should have the results here at the bottom for everything. So what happens in Xilinx? Synthesis doesn't do anything. So depending what file do I touch, it's not very deterministic, the synthesis time, so it has some random noise. Placement is able to optimize. So sometimes it's going to consume like half of the time, but sometimes it's 0. It does a pretty good job. And on routing, it doesn't do. It reduces a little bit, at least not in the middle, but sometimes it has big noise. It's not very deterministic in time, not deterministic. Now in Quartos, the place and route is nothing. It doesn't do an improvement. It's in the noise. And I was talking to the engineers because there is nothing there. It doesn't do anything because there is nothing in the code. But they try to do on placement and synthesis. And on synthesis, it's very systematic to get around half the time. And it doesn't do much more. No. And here, remember, there was no code change. So that's it. No? Yes?
This is for a single design, right?
That's for a single design, but it's representative of what happens.
Why is there, for instance, for flow 1, for place, why is there a range there? Wouldn't you expect the tool to either understand that this is the same thing and go fast, or redo the whole thing, or redo half of the thing? I'm just curious why there's a...
So what happened is that the place is fairly fast, and most of the points are there really, but there is some that it go to 0. And I'm not so sure why a few were able to go to 0. Most of the time it was just doing traversal, checking that there is nothing and it stays there.
Were you touching different files?
We were touching different files, yes.
I see.
And maybe because it was re-elaborating one design, it was not able to reduce the time, but it was resynthesized and everything. So I'm not so sure what exactly it did here. The problem with those tools is very opaque, so I cannot have a visibility of what's going on inside.
Are you using partitions on Flow?
No, this is the design. There's no partition or nothing. And when we do
that could actually save you a little time if you turn it on, because the partitions will cache the synthesis results.
So I think in this one there is no partitions, because what we are doing is like synthesizing one design. If I were cut and pasted many of the designs, I would have done that. Yeah, but if there is an array or something, but here there is no such thing.
Judging from the times, this seems to be relatively small.
Yeah, it's a small block. If you do bigger, it will scale. But now, what tend to be the changes in local when you are edit? So, what is our idea of a flow? Is that you synthesize during the night, and during the night it does a full synthesis. When you come back in the morning, you get your coffee, and then you start to work, and you're going to do little changes. You work with incremental, and then you commit your changes or not, and then we do a new synthesis in the night. So when you are doing changes, most of the time your changes are local. Yes, you can change a define who does a search and replace all over, and it will change everything, but most of the time, if you are in a debug loop cycle, it's not the type of thing that you are doing. So if you do a simple example, this is too trivial, but it's in order to visualize what happens, is that you are going to generate some, after you do the change, you're going to do some elaboration. And then you are doing some code change, and you're going to have a different elaboration, and technically it's a different gates that you are going to have. So what is the thing that we did? So we went through the internet. So the first is like, how do we benchmark this thing that we're going to do? So what we did, we went over the internet, we looked for any verilog project in which they were open source, and they were commit history. And for every of those projects that we can, that there is more than 30 patches that we can apply, because sometimes there were 2 commits, so I cannot apply, there is not enough representation. So for anything that they were having, I think the threshold at the end we reduced because there were too few, 15 patches. So then what we do is on the repo, we look what were the commits, and we were going to reapply those and to see what is the time it takes to synthesize. So that's the way that we get, is this representative, is this valid way to create a bug or not? So what we did is we look for repositories, open source, deltas, and then we'll reapply. For example, here is a fix this MMU translation. So we create an ifdef, and we enable and disable this patch, and that's our incremental synthesis. A simple one line of code.
What's the criteria for what you define as an incremental change?
For the problem is, what is our benchmark? I can create synthetic cases.
No, I get what you're doing. You're taking code, off-the-shelf code, but you're saying like.
So what we have
different pull requests or different commits, or.
So every commit, it will be an ifdef, and then I can enable and disable that commit in the code.
Okay, so you tested incremental commits.
Yes.
Okay.
It's one commit at a time. And for example, a trivial thing is like if I have this line, so we have enable and disable this line. So what is the time that it takes me to resynthesize because I did this?
Did you try batches? Like at what point?
Combining commits.
Like, okay. Well, the point was that the real question behind that is like how big of a delta can you handle?
So in theory, you should be able to handle anything. There is no constraint on the size. The more that you have to resynthesize, the more time the corner logic that you're going to have to synthesize will be more time.
Well, I'm thinking more like the more disruptive the change, the more you have to do global optimization.
We do global optimization. We don't do local. It propagates to global. So how is our general flow? So what is the principle? So we do, during the night, when we do the synthesis for these numbers, we even flatten the design. So we get the ASIC, because this first set of numbers is going to be for ASIC. We get the design, we flatten. So there's optimization across everything. And then we synthesize overnight. Now, after it's synthesized, we are going to look and partition that graph. It's a giant graph. We're going to partition a graph in which there are going to be points in which the optimizations are not going to propagate. If I do synthesis, there was no propagation of optimizations across. I'm going to explain a little bit later how to do this. But conceptually, what I do is, after the whole thing is synthesized, I have my elaborated and have my optimized netlist. And I look at my optimized netlist, and I look for boundaries on that graph so that the optimizations did not propagate. If I see that there is anything on the critical path, I will join those blocks. So I'm going to allow to grow the graph. But I create subgraphs. And then when I do the incremental synthesis, I'm going to be restitching 1, 2, 3, 4 of those graphs. Depending how big it is, I'll do more. In theory, I can even do them in parallel if there are many incremental commits. That's something we are looking, but on the numbers that we have, we don't do that. So what is the outline that we're going to go? I'm going to go over live synthesis, and I'm going to show the results that for ASIC first, but then later I'm going to show for FPGA. And then we're going to do the place and route for FPGA, and I'm going to talk about simulation too. Now I'm not only doing synthesis, also simulation. How do I do incremental? So live synthesis. So the overview of the flow is, we have a setup phase that it runs during the night. We get the HDL, which is verilog. We do an elaboration. Elaboration is very fast. It's just traverse over the verilog and generate a netlist, not optimized. And then after elaboration, we save it. And then we do synthesis. We flatten the whole thing, and we trigger synthesis. If we didn't flatten, it's going to be even better. And then we do place and route. On this first part of the work, it's only the synthesis. So what do? During the night, we have our setup phase that is going to look the netlist after elaboration and the netlist after the synthesis, and it's going to look for boundaries that they match each other and places where there was no optimization across the blocks. And then when you are working during the day, you do changes on the synthesis. We elaborate only the netlist, the module that you have changed. We look for the difference, what subgraphs needs to be resynthesized. Then we resynthesize those ones and restitch them again. So the first thing is, how do we look between the elaboration and the synthesis? What is the thing that we do? So the synthesis tools are helping us in that way. So in this flow, we run DC, Design Compiler. But we have done the same with ABC, which is the open source flow, or we have done the same with Vivado. Not Quartos, sorry. It should work, but I have not tried. So what do you do on those ones? After the tool synthesizes, it tries to preserve netlist names. And the reason why it tries to preserve the netlist names is because for the SAT solvers, if you don't preserve the netlist names, you're going to have a very hard time. So if the netlist has not been optimized, it will try to preserve the name. So based on that, and then we are doing things like functional decomposition, minor tweaks, minor optimizations around that, we're able to partition the netlist. But it's a heuristic-based partition. So we find, for example, here is a poster child kind of example that is too small. If we have this netlist, we say, oh, these netlists have not changed, so it's going to be the same. So hopefully these gates and those gates, they represent the same functionality. I say, hopefully. We don't know if we pick the correct place. So the thing that we have to do, we have to run a SAT solver for each one of those blocks to verify that we are correct. So we do this, but for the moment, we have not found any time that the SAT solver fails. So it's always correct what we find, but we have no way to prove that it's always correct. So technically, you have to run the SAT solver. Yes?
So far, this seems to apply to combinational logic changes. Are you also going to address, having pipeline?
So if you add a new pipeline, so it will propagate through the netlist. For me, it doesn't look any change if you add pipelines, flops or not. In the netlist, I treat the flop like if it were a gate. It will propagate or not, just keeping preserving the names. So I don't do any optimization looking, oh, this is an app, or not. Just a net, it's really a graph. I don't even look what's inside the node. But then later I have to remap back and I have to do the SAT solver to verify that it's correct. If it's a flop, the SAT solver will remove the flops and it will set as inputs and outputs and then SAT solver verify. But that's independent of what I'm doing. It's more the verification flow. And that's already working for us. So this is slow, but it's only done once during the setup during the night. So what do you do after you have this netlist? You have the original elaboration netlist and the optimized netlist, and you have divided the whole graph in subgraphs. So when you do a code change, you elaborate very fast. And after the elaboration, you are going to do a structural traversal, because I could compare and doing a SAT solver to minimize the changes. I want to go fast, I cannot do that. So I do a structural traversal to find, has this elaborated netlist changed in any way from the other one? And I'm very conservative that many times I trigger and say, oh, a change, but in fact there is no change. But I'm conservative in order to go fast. The only thing I have to do is to traverse the graph or the re-elaborated things. If there is any change, I find that there is a difference, so I resynthesize that subgraph. And then I will restitch. So I'll trigger the synthesis, and I only synthesize this. If after synthesis I see that there is a new critical path as a result that it propagates between the inputs and outputs, I reattach it with the surrounding netlist, and I resynthesize the whole thing. So there is global optimization. But that will happen only if, because of the change, there is a change on the critical path on the result.
Doesn't that propagate all the way up?
It could propagate all the way up, but in reality it does not. So to avoid the worst case potential thing, you submit the full synthesis in parallel. So the worst thing that's going to happen, I just use the full synthesis. In reality, it is not the case. But technically, you can do that. So what is the typical size? How many gates are we synthesizing? Well, it depends on the block. It depends on the patch that you apply, no? So what is the typical cone size? So for those blocks, this is not for the bugs applied. This is for the total graph. And let's assume that you equally randomly patch one of them, no? So if I do the FPU, so let's put it in this way. If I do less than 1,000 gates, it's everything. I will have to synthesize less than 1,000 gates in order to do, if I touch only one of those Konos logics, those netlists. And most of the times you only touch one. So it means that I will touch, we'll have to resynthesize 1,000 gates and restitch it back, and that's it. Now, if I do some other designs like the MIPS R10K, there are more, but it's very rare to go over 6,000 gates that I have to resynthesize. So most of the time I need to resynthesize very few gates. For this other core, it's different. So every design is slightly different. So why was more in this MIPS core? It's because it was an FPGA implementation. We're synthesizing for ASIC, and they did the divider in a single cycle because it was not optimized. And we were doing DC. So there's a lot of paths, and there's a lot of logic, very critical. That's the reason why they have so many things around here. If you do a design that is more optimized for frequency, in fact, it tends to be less. So it depends what you have in your design. Now, how does it look, the synthesis on DC? And this is going through DC, which is not very fast, going through the TCL interface on DC, because it's the only thing I can do. So what do I have here? I got one of the designs, and I have all the bugs that I reapply. So what is the thing that I have? This is the time that it took me to synthesize with DC. So typically it's under 1 minute. The worst case was 5 minutes. And the baseline was 29 minutes. So it was 30 minutes to run with DC for that design. It's typical 1 minute, that is 5 minutes. Technically I can have a bug that I think that triggers 29, no? But in our cases, all the commits that we have, it didn't. Now, those are supposed to be commits from people who did, so they are supposed to be representative in a way. What's representative is, one of the things we are doing is creating a benchmark for incremental so that at least the people can evaluate and they can compare the same things. So if you know any open source or anything that you might want to release that they have commit histories of bugs that we can reintroduce, we can add it to the repository so that people can evaluate and optimize for this. One of the things that we're trying to do is to add OpenCL projects there. So that's in our to-do. And to add chisel generated code, like a boom out of order code. So what is the speed up result? So here it's a little bit tricky because we are comparing this design compiler. And there is nothing on the design compiler. So what did we do? So we implemented quartus and compared quartus versus quartus in incremental. So what is the speed up that they get for some of those blocks? Then we implemented a paper that is called LLIR, is what we think is the best on the state of the art on literature. And we implemented that, and then live synthesis, that is what we have. So it's the speed ups. Obviously, it was a paper, so we are always the fastest. You always do that when you are doing a paper. But really is that we have around up to 80 times the speed up on a single piece of code. On average, it's 10 times faster than the competition. And it's from 30 to 3 times the speed up. So what about the quality of results degradation, QOR? So this is looking at the frequency, but it was similar results for power. So what do we do on the benchmark? So we do something that we thought it was unfair to us, so but it's okay. So when you resynthesize, even if you do no code change, you can go faster. Or sometimes you go faster than the full synthesis. Whenever we are going faster, it shouldn't be, but the tools are not very deterministic. Or the optimizations, because we are targeting a different optimization, we can go faster. We say we go 0. So we discount the going faster. Whenever we go slower, we go less. That's the reason why the 0 is so big. It's not that we were exactly the same, it's because sometimes we were faster. So we have here a big 0. Now, what is the worst difference that we got? In MIPS, we got 4% frequency degradation in some of the blocks. This is the histogram, so you see that it really happens once. Most of the time it's in 1%. And that's putting the speedups as 0. If I do a Gaussian distribution, it was more or less centered on the 0.
This is synthesis-based
DC.
Frequency. Yeah, okay, DC.
DC full flattened design, comparing incremental versus not incremental.
So these percentages, at least I would think these are within the noise, right? At that level.
That's the whole point. Is that there are little changes, but the fact that we resynthesize is in the noise level.
The other thing that's kind of interesting is that there's a bias in your data points, because I assume that as a project progresses, they might be improving things in terms of time.
No, here I'm comparing to avoid that bias. So there were 30 bucks, we did 30 full synthesis. And when we compare the delta, it's with the delta with the full synthesis of that block. So in theory, it should be the same if it were deterministic table, but it's not, because we synthesize a sub-block. So we don't compare versus the baseline. We do 30 full synthesis. There are 30 bucks, 30 patches. We do 30 full synthesis, takes a little time, but for benchmarking it's okay. And then we compare with each one of those, the delta versus this one. Because sometimes you go faster, don't go slower, otherwise like what's going on. So this is not how much faster or slower as the patch, is the delta versus the patch. So this is for ASIC synthesis. What about FPGA? So this is under submission for ICCAT, but fine, can talk. So the Altera Intel is not a great job. And those are the slides that I used recently in Altera, Intel, and Xilinx. So what does remember the slide that we had before? This is the Xilinx, this is Altera. So here there is nothing, just improving a little on synthesis. So for place and route, 0. So what we did on this work, we went through the vivado flow, and we went through the tickle interface.
I just have one more question about that graph. I just noticed that on the Altera flow, the time spent in synthesis, is it just that the measuring of time is different in these tools? Because how?
So it's the same design, it's the same thing. So the the vivado has an analytical placer. It's a little bit better. So in placement is much faster than Altera even doing the same thing. Routing is more or less the same, a little bit worse. And on synthesis, there's very little difference, but it's around there. They are not the same, even though they are supposed to be the same in the very equal quality thing. But the analytical placer from vivado is better than the one from Altera.
I see. When you say better, do you just mean faster or better results?
That one is a little bit trickier to compare because it's different FPGA platforms. I don't know exactly what the Altera does. I know more of the vivado. It was purchased from a professor from San Diego. Not San Diego, now it's in San Diego, Andrew Kahn. And he was, it's a pretty decent placer. I'm not so sure what Quartus is doing. So I will not be surprised that it's also better results. That's vivado. You're using ISC? No, the opposite. I will say the opposite. But that was one of the main changes that they did from ISC to vivado. It was to change the placer. So what is the goal here? So what are we going to do in the optimization? So we have the incremental synthesis, as mentioned before, and we have some tricks how to optimize more, but we didn't optimize more. When you generate an FPGA, what do? You program a LAT. And in the LAT, I don't care if I do an OR or I do an XOR, it's going to still be the same LAT. So I don't need to replace the LAT if I only change in the program in my LAT table. I to replace that guy. So we look if the structure of the LAT placement has not changed. So I just changed the LAT program, but I keep the same connectivity, the same structural mapping, and that's what we do SM. I don't have the name here, but we call it structural map for FPGAs. So I don't need to replace and reroute. So what we do is we synthesize, we reduce the search space, and then we do a T-map. We look which ones are exactly the same, only changing the LAT, and then we create a tcall command, which is not fast, but even with that we get good numbers, and then we replace only those ones, because in the vivado there is an incremental placement option. There is no such option in Quartus. So I can tell replace only this gate, and reroute only this, not this gate, this LAT. Reroute only this LAT. So we go through the tcall interface and we do this. Yes?
Do you only look at the LUTs or do you look at other elements that would?
So the other elements, if they got changed, it will get replaced. So it's a design that might have SRAMs and everything, but the optimization only looking at the LUTs, because replacing a memory bank, it will not be as costly as doing gazillions of LUTs.
So I didn't quite catch the bit about the difference with Xilinx and Altera. So you said in Altera you don't have as much optionality in terms of just
there is no, and I was talking to the engineers, it's not that there is no option, it's that it does not exist internally. So you cannot trigger, even if I'm in engineering inside Intel and knowing everything, replace only this gate, this LUT.
So in Xilinx, you can go, like if you could just repurpose an existing LUT in Xilinx, you can just go in there and change the entries directly.
Yes, through the tcall interface.
No way of doing that.
There is no such functionality, and even if you are in engineering inside Intel, you cannot do it because the flow internally cannot do it.
First engineering the bitstream.
So you can do things like that, but it's not.
I'll take it.
So these results are using their tcall interface, not really playing with their placement. So we think we can even do much better than what they are doing even for placement for those individual LUTs. And the reason is because there are, and that's something that the student is working to submit for ASIC, but it will work the same for FPGA, is that those placers are analytical placers. What you do in analytical placers, it's several iterations. It's until it finds convergence. When you do an incremental, you could reuse the previous results in order to converge much faster. They don't do things like that. You have a lot of tricks in order to speed up even way more the placement information that you have there. So what are the things that we are doing? So we do the elaboration. So on this one, for the elaboration, we do JOSIS. It doesn't matter because that is a faster elaboration and we have a better, tighter control. This is the time they take to design. There are several blocks, and this is the average across all the bugs. So when we do the elaboration, it's a few seconds. Now, on top, we do the difference across Netlist. It's very fast. And this, by the way, it was our previous version. We were using Ruby. So this is doing Netlist difference in Ruby. Now we have a C++ version. You cannot see it. It's just a line. And then to the same thing, the synthesis, we trigger the resynthesis. But because we resynthesize so little, most of the time it's gone. So most of the time is really the elaboration. Now, without the structural match change, but applying the incremental synthesis, we can resynthesize only a small set of places, LUTs. So how much time does it take to place? In around 40 seconds. And then route is the rest. Now, when we do the structural match, we get the results out of this. So we're under 30 seconds going through typical interface, and in many cases a little less. So this was taking around 20 minutes when you do vivado. With vivado with incremental, it was taking under 20 minutes. So now we are in under 30 seconds, and that's with the typical interface.
Vivado has a guided route, place and route. Like you used to use previous place and route.
So we don't vivado and we enable all the incremental flags that they can give us. But what happens why they are not doing such a good job is because they were doing a bad job on synthesis. So and then it triggers a big chunk of recompile, resynthesize everything. So each one of those tools have a problem. But this generates a bitstream and you are ready to upload. We don't include the time of the bitstream generation on this one, but this is after place and route. It's just bitstream generation that is left after. If we were having our hands in the full flow, we can chop this less than half. And one thing that it was not left is the structural match, how much time it takes, and it's because it's our Ruby traversal. So what are we doing? We are trying to improve the productivity when you use the tools. For ASIC and FPGA, to have very fast, quick iterations. This, on the ASIC, it's not that you're going to fabricate the chip with incremental, it's that you can get feedback on the timing. It might change in timing, representative, how do I keep improving? That's the goal that you will have for an incremental ASIC. For incremental FPGA, it's a little better because you can create the bitstream and then you can upload the bitstream and run something and see if it doesn't work. No, it doesn't work. I will not use it for deployment, but for debugging and development, I will use that. Now, when you do the final deployment, fine, just submit your gazillion simulations with gazillion of seeds, pick the best, and submit that for your deployment. But when you are doing the development cycle and testing in your FPGA, this really improves your productivity. Now, what is the other thing that we are doing? Something similar, but for simulation. So we are building a hardware description language in Santa Cruz, and we are trying to make it more productive. One of the main focuses is be more productive on that hardware. The talk that I'm having here is for simulation, but it should work with Verilog. The only thing we have not done it because we have done for our language. Conceptually, there is no difference. So what is the thing that we have? Is a checkpointing and hot reload. This is submitted for micro. There's a question mark because still in review. It can get rejected, who knows. But what is the goal that we have is under 2 seconds hot reload for simulation. So you run a simulation, and remember, I'm a computer architect. I love out-of-order cores. So I build out-of-order core. I run my simulation for very long. It takes billions of instructions. Now I have a bug. So I have to recompile and rerun. As a reference, so I do consulting on the Valley. And I know, for example, in Apollo or some ARM server CPU, you do a line change, trivial. You to make with VCS, it takes you for something like the Apple A11, 20 minutes to recompile, to run Hello World. That's the design flow for the Apple engineers. The same for the ARM engineers in another company. And this is just printing Hello World. As a result, the engineers, when they are running simulations, they have a bug. They do several directories, they do several components, try several things at once, and you try to multiplex your time, because otherwise you are drinking too much coffee or whatever you are doing. So what is the goal here? You run the simulation. As the simulation runs, we checkpoint. In our case, we checkpoint every 10,000 cycles. Why 10,000? Because I have a previous paper, and I've been looking internally on the bug reports for those companies. And it's very rare that you have the source of the bug and the detection on the bug beyond 10,000 cycles. Most of the time, you capture in the 10,000 cycles. And I'm talking about the tricky memory consistency bugs. Technically, it can be something happened a million cycles before. Most of the time, tend to be in the 10,000 cycles. So every 10,000 cycles, we create a checkpoint. Now, as you run the simulation, you are going to trigger an assertion, so the simulation stops. But you have your checkpoint. Then you go back to your checkpoint, you change your code, and you replay from that checkpoint. So it's hot reload, and you replay. Changing the code from the moment that I edit the code and I hit save until I have replayed my 10,000 instructions, recompile and everything, is under 2 seconds for all the code changes that we had tried. So what we do is we create checkpoints, we're able to replay. We're able to create many checkpoints from the past, so that a very useful feature is that many times when you bring an SoC, you have a lot of simulation time that it's not that way you are testing, but you have to rerun it again. So because you have the checkpoints, you have many of them, they will be checked in parallel, nothing cross-check, so you are reproducing the simulation in parallel until the point in which you start to have changes. So, yeah?
So if you introduce new state, though?
We are allowed to introduce new state, remove a state, and do things like that. When you add a new state, what we do is we introduce very clear, simple policies that are easy for you to debug. Whenever you introduce a new variable, it's initialized to 0. If you rename variables, we're able to track, and it gets whatever is the original value. If you delete a variable, who cares? It's gone. It doesn't affect your state.
Following up on that, even if you make a small combinational change, that could change the storage.
The storage. So what happens for debugging? For example, imagine that you have a bug in the memory consistency, no? Because it's what I was looking many things. So because of that code change, it might have some ripple effects. But many times to debug on thing, just replaying from the last 10,000 cycles is very useful, and you can solve this one. If it has ripple effects, we replay all those ones in parallel, and it checks in parallel if there was any difference. If there was a difference, it will tell you, and then you will know, oh, there's a difference, and you modify only here. Do you want to reflow the whole thing or not? And it will reflow only from the point that it starts to diverge. So for example, if I do something that I bring the SoC, and then I change my reset vector to the CPU. So bringing up the SoC is going to be the same. After resetting the vector, reset of the CPU is going to be different. So from that point, I will start to reflow if I want to. But I will be able to detect from what point.
If I reload, then I guess we can say that this gives you a good, with a good chance, if you reload and the bug is solved with the change you made, the bug is fixed, that means there's a good chance you fix it, but you really know you have to rerun it.
Yes. But the whole thing, while you are doing the whole thing, it will be rerunning in parallel.
Okay.
Because, I don't care about CPU time. So submit everything to the cloud, and it will run all the things in parallel. The checkpoint don't go to the following. It will notify you as an error. It start to reflow, re-execute from there without checkpoints. So we do checkpointing, and we do many other things. So now is your simulation very slow or not? So if we do hot reload, so what do we have here? This is the simulation time, and this is the total number of cycles where you want to restart to re-execute. If we do hot reload, it's always 2 seconds. No? So this is not the point of this graph because it's a very boring flat line. The point of this graph is how much time it takes to compile, how much time is the simulation speed. If we do the live sim, and this is a 16-core RISC-V, and it's, you do some code changes there. If you do the live sim, we start from 2 seconds because we're compiling under 2 seconds. And then the slope of is the simulation speed. If we do this line, it's verilog. So verilog has more time to compile, and the slope is higher, it's slower. So we're faster than verilator, and we compare in less time than verilator. So we're around 2x faster than verilator. Why are we faster than verilator? Because verilator, which is very fast, has an instruction cache footprint when you do designs that are not trivial. Many of our optimizations to optimize for fast compilation, it has forced us to reduce the code size that we generate, because otherwise we couldn't generate so much binary in very fast time, in 2 seconds. Otherwise we couldn't do this thing. If I start here, I'm already toasted. It's not my 2 seconds goal. So all those things have in fact improved our simulation time. Not if I do a trivial GCD. Now, verilator as a reference is fast. I'm not so sure. Did anyone here use verilate? I don't know what you use here, but BCS, for example, running something like Boom, it runs, I think it's around 500 hertz. The simulation. Boom is an out of order RISC-V core. In verilator, it's around 4-5 times faster. Now, why it's faster than BCS? It's not that Synopsys people are dumb. It's that verilator does only 2 states. It doesn't have X and Z's. It's optimized for synthesizable logic, and whenever you have an X, it does a random number. And it does some other optimizations in your design. So what's the live status that in Santa Cruz? So we have the paper live synthesis. That is what I was mentioned before. It's at DAC 2017. We have created a set of benchmarks for incremental synthesis. So if companies or anyone or doing papers want to benchmark and compare, at least we have a similar platform. And we call Anubis. We have an ASIC automation with FPGA numbers that I was mentioning, with more details how to build it. We have this hardware accelerator for performance feedback. That's the live simulation thing. It's a micro submission. Now we have another thing that we are working is for live ASIC placement. So incremental placement for ASIC. The same technology can be applied for incremental placement for FPGAs, but we keep switching back and forth, FPGA and ASIC. So we are going back to ASIC, but we could do FPGA if there were more interest. And then I have a student, it's a new student, so DAC 20, who knows when, to do incremental routing. And we do SAT solvers to do this. Now, one thing that I'm not so sure how many time, but that I'm also been working is PyROP. It's a new HDL language we're designing. That's my license plate. So I got the license plate on the car and told the student, now you cannot fail on the project. It's like going to be shameful if I have my license plate for a failed project. So what is the live summary? So what is my hammer? Live development cycle in 1 to 20 seconds goal. And I will apply this to anything that it takes my way to design my future out of order core. Someday I'll go back to that. And I apply it for ASIC, for simulation, for FPGA, for performance simulation, for everything. I don't do quality degradation. So I'm not willing to have a performance loss because I do this. I don't do approximate models. Approximate models are an alternative way to do it. That it makes sense, but that's not my approach. You could do an approximate model, provide you feedback. For the FPGA generation, I don't see how to do it, but for the ASIC, it makes total sense. In my case, I do the real thing. Just try to reduce the problem size. Get a good, fast incremental. So the other things we're working is in the new hardware description language. I'm not sure are we on time, so I can show you a little bit. Otherwise, we can talk later for people who might be interested. I'm trying to do a open source flow for synthesis. It's integrating things that are outside, but we are having the new database. It's a graph representation memory map, very fast, efficient. And the reason is because many of the optimizations to do in incremental, we need to have our hands on in the database representation, the graph. So we are building all these things and we're integrating. And the goal is to release open source. Google is interested on this, and they are going to use it this summer for parallel synthesis. But the goal is should be released open source by summer or slightly after summer. But it has to be before summer because otherwise Google cannot use it. So you have any questions?
think most questions got asked during the talk. Okay, let's thank our speaker.